It's rate of change today. Rate of change. It's miles per hour, or gallons per minute, or meters per second, or pounds of turkey eaten per Thanksgiving Day. Anything you can think of. We're talking about rates. Okay? A rate of change is a rate that describes how one quantity changes in relation to another quantity. Miles, like I said, miles per hour. Miles, however many miles you're going per however many hours you're driving. So one quantity is our miles, and it's changing in relation to the number of hours traveled. Okay? By the end of today, we want to be able to say, I can find rates of change. Okay? We're going to figure out how to calculate rates of change. Secondly, which means, since it's a rate of change, it's probably going to be some sort of fraction or ratio, okay? Because it's going to be some sort of miles per hour or meters per second, something per something, right? And we also want to be able to say, I can interpret rates of change in different contexts, okay? So let's start out with an example. The table shows the growth rate of subscribers to satellite radio. Find the rate of change from 2003 to 2005. Now, find the rate of change. That means, what are our two quantities? Total subscribers, so that means total people subscribing to the radio, and years. Okay, so we put a little clue right here to help you guys out. If you're going to find the rate of change from 2003 to 2005, on top you're going to put, hey, how much did the subscribers change by? How much did we grow or shrink? So in 2005, we had a total of 7.7 million subscribers. In 2003, we had 1.8 million. So what I'm doing here is I'm finding the difference between what we currently have, well, what we had in 2005 and what we had in 2003. I'm finding the difference so we can see, obviously, the number of subscribers grew. I'm trying to find out how much that number grew by. So 7.7 minus 1.8 will give me that answer. Also, on the bottom, I'm putting the change in time. So that's really pretty simple. 2005 minus 2003 is only going to give us 2 because that's only 2 years time, right? So maybe I should actually label these things. So 2 years, because this is, well, I'll erase that. That's years on the bottom. On the top we have subscribers. So that's total subscribers. I won't even write that in. 7.7 minus 1.8 is going to be 5.9, and this is where I'll write it. 5.9, and I'll write it. Subscribers. Actually, it's 5.9 million, because this says it's being measured in millions. 5.9 million subscribers every 2 years. We don't like hearing that, though. We like hearing per 1 year, or per 1 hour, or my car drives 31 miles per 1 gallon. So we want to find the unit rate. That means our denominator, we want it to be 1, right? Okay? So very simply, we just do 5.9 divided by 2, and we end up with, or we should end up with, about this thing right here. 2.95 million subscribers, or million people, per 1 year. I'll write that out for you guys. 2.95 million subscribers per 1 year, or people per year. That is the growth rate. Okay, that is the rate of change from 2003 to 2005. The number of subscribers grew about 2.95 million people per 1 year. So you just found a rate of change. A rate of change can be increasing, it can be decreasing, it can stay the same. If I had, I don't know, 12 pairs of shoes last year, and this year I still have 12 pairs of shoes, well, I didn't lose any and I didn't gain any, so the rate of change in terms of number of pairs of shoes that Mr. Dudek has stayed constant. It stayed the same. Let's take a look at this. It says rates of change can be positive, like I said. If your rate of change is positive, your graph is probably going to have an upwards slope. Okay. If your rate of change is negative, let's say we had less subscribers in 2005, maybe this number dropped to 1.2 million. Okay, that means we lost subscribers. That means our rate of change was negative. If you were to graph what this would look like on a graph, you'd see a line sloping downwards. And lastly, if there is zero slope, if nothing changed, like in my shoe example, okay, you'd see a straight line straight across a horizontal line. Okay, rates of change are important to us because predictions can often be made. However, predictions can really only be made fairly accurately when the rate of change is constant. Okay, a lot of times the rate of change is not constant. But let me give you another example. If you did push-ups for 5 minutes, 5 minutes straight, I just said give me push-ups for 5 minutes, your rate probably is not going to remain constant. In the first minute, you might get 30. But then in the second minute, you might slow down and you might only get 10 or 15 because you'd really start to get tired. And then you might really fall off in the third minute and just be struggling to hold yourself up. And you might only do 5. Okay? That rate at which I'm doing push-ups is not staying constant. Okay? What you're actually going to see there is a negative slope. As time goes on, as you get further and further into the 5 minutes, you're going to do less and less push-ups. You're going to do them slower and slower. Okay? So if that rate of change is constant, it makes it easier to make predictions. If I could do push-ups at the same rate for 5 minutes and I can do 30 push-ups per minute, well, I'd be able to do 150 push-ups in 5 minutes. Let's jump down to number 2. The data points on the graph show the relationship between altitude and temperature. Altitude is your height. Okay, so if I'm like up on a tall mountain, I might be up really high. If I'm not, or if I'm down in the Grand Canyon, I might be at a really low altitude. I might actually be what we call below sea level. I might be in the negative kilometers because we always measure from sea level. Sea level is like our zero. Okay, it's our middle point when we talk about altitude. So we have our 2 data points here. We're only given 2. So 0, 24, talked yesterday about what that means. Since our x-axis represents our altitude or our height, that means at sea level, at 0 kilometers high, the temperature might be 24 degrees Celsius, okay? Because our y value is 24, and our y-axis is representing our temperature, okay? So 4.2 might mean, as you hopefully would have guessed, that if you're 3 kilometers above sea level, it might only be 4.2 degrees Celsius, okay? We're, of course, assuming the same day, the same area. Okay, we're not talking about someone in Ohio and someone in Alaska. Okay, climates differ there. We're talking in the same general area on the same day at the same time. If you climbed a mountain and you climbed 24 kilometers up, I'm sorry, if you were at sea level, it would probably be about 24 degrees. But if you climbed 3 kilometers up, yeah, your temperature is going to cool off as you climb up, as you get higher. So a couple hours later, it might only be 4.2 degrees. Now, that's not even answering our question. We're asked to find the rate of change. Okay? So let's talk about this for a second and get my pen working. Since we're looking for a rate of change, a change in temperature. So, for instance, maybe we're talking like 10 degrees per kilometer or something like that. But I'm going to write this. That's not the answer. I'm going to write this out so that we can see it, though. So a change in temperature over or divided by a change in altitude. Okay, this is really what we're looking for. Or actually, this might make it easier. Well, I won't even talk about that right now. Okay, so you can write this in a different way. I'm still going to write that equal sign. You can also write this as y2 minus y1 divided by x2 minus x1. This is the shortcut to finding the rate of change between 2 points on a graph, or 2 coordinate points. So when I say y2 and y1, that really just means the ordered pairs that I'm talking about. If we call this point 1, this would be labeled x1, comma, y1. Those are not exponents. This is just telling me that this is point 1, and this is, if I made this x2 and y2, that this is point 2. It's just so that I can distinguish between the two different points, point 1 and point 2. So if I do that, and it does not matter which one I choose to be point 1 and which one I choose to be point 2, that's up to you. So if you wanted this to be x1, y1, that's fine. Then this would be x2, y2. But it makes this very easy to find the rate of change, because we can just plug in the value that represents y2, which in this case is 24. I can just plug it in for y2. So check it out. This is going to be 24 degrees Celsius, right? Because that's what 24 represents. 24 degrees Celsius minus, what is y1 in this case? It is 4.2 degrees Celsius. Okay, great. It's divided by x2, which is 0 kilometers, because that's our x value. And our x value over here is 3. So 0 kilometers minus 3 kilometers. Why am I subtracting? Because this is the formula that we're using, and it's built in. It says, hey, you're taking the first number, the first x value, and you're subtracting the second one. Okay. Now, let's just simplify this a little bit. This could be 19.8, excuse me, 19.8 degrees Celsius divided by negative 3 kilometers. So like we said up top, we do have our change in temperature, 19.8 degrees Celsius, per every 3 kilometers that you go down. That's why it's negative 3. However, like we said before, we don't like saying per 3 kilometers. We want to know per kilometer, or per minute, or per second. So I want to find the unit rate. That means actually perform the division, and you should come out with negative 6.6 degrees Celsius per what? Per what? Per 1 kilometer. Okay, that means every kilometer that you go up, that you hike upwards or fly upwards, it's going to be 6.6 degrees less, or 6.6 degrees cooler. Okay? So as you climb up, if you notice on our x-axis, the further we move right, means we're going up higher and higher in kilometers. The further we go right, the less and less the temperature is. It gets lower and lower. So our rate of change is this. Okay, folks. Rate of change is it's a very useful tool. So let's take our time. If you need to, take a minute or two and go back and listen to some of this again. If you don't like this formula that I've thrown down here, then just do this. What's your change in temperature from this point to this point? Basically, all you'd have to do is say, hey, I'm up here at 24. Now let me count down. That's 2, 4, 6, 8, 10, 12, 14, 16, 18. Almost to 20, but a little less than 20 because this is 4.2. Okay, I had to count down 19.8 to draw even with this point right here. Okay, so I had to count down. So my change in temperature, since I went down, you would have said it was negative 19.8, And then what's my change in altitude? Well, altitude is represented on the x-axis. So let's start here. I'm even with this x value, with this point, and let's count to the right. Okay, there's a difference of 4 here, and I went to the right, so it's positive. Look at that, 19.8 divided by, oh, excuse me, it's 3. Silly error, Mr. Dudek. This is 3. So 19.8 divided by 3 is going to give us the same exact answer that we already got. So if you prefer to count, please do so. So just count down. That means you move negative 19.8, and you move to the right, which means a positive 3. Then you get your rate of change. Make sure that you label your units. Alright guys, I will talk with you tomorrow.